Okay, so we're now ready to talk about the linear probability model. This is the simplest possible model for binary responses. The model in which we model the probability for y equal to 1 conditional on x as a linear index. Okay, so here x is a vector of explanatory variables. There may be like k of them, and then beta here is a vector of coefficients with also k coefficients. So that's the simplest possible model we can do, right? Have just model let g be a linear function. Now, the nice thing about that is it's also a model we can estimate with OLS because it's a linear regression model. Because of y being a binary variable, we know that the mean of a Bernoulli distributed variable is equal to the probability that it's equal to 1. So in this case, we really have a regression function, E, or the expected value, conditional expectation on y given x is equal to linear index. And we know how to estimate those models, right? This is a linear regression model. So how do we do that? Well, we use OLS, okay? It has a nice closed form expression for the estimator here in matrix form, x prime x inverse x prime y, where those x's here are really just n by k matrices of observations of the k explanatory variables for all the n observations. And y here is n by one vector of binary outcomes, observed binary outcomes for all the n observations. Okay, so I apologize for this unforgivable abuse of notation that I didn't introduce this, but I guess you know how to do OLS by now. Okay, so it's clear that this is pretty easy to estimate. Okay? So that's one of the main advantages. One thing that also turns out to be an advantage is that it's actually a pretty good approximation of the average partial effects. So if you estimate the partial effects for all the different individuals in the sample, and then average over all the observations for all the different people in the sample, well, then you get the average partial effect. We'll talk about that later. But actually, our estimator beta hat is a good approximation of those average partial effects. So if your interest is in calculate kind of the average marginal response of a change in an explanatory variable, well, then beta is actually the OLS estimator, or the linear probability model gives you a very nice approximation to that, even within this simple framework. So that all sounds pretty good. There is some issues, and the main one is really that the predicted value of the response variable and the predicted probability for y equal to 1 is not restricted to the unit interval. So what does that mean? It means that you can have probabilities that are larger than 0 or negative. Okay, and we don't like probabilities that are negative generally. Okay, so that's kind of a caveat, and you can immediately see it here, right? If, say, for instance, beta is positive and you let x increase, well, eventually x times beta is going to be bigger than bigger than 1 if you're doing counterfactual predictions, and sometimes it's even the case within the sample. Okay, and yeah, we'll see examples of that just later. Then another thing here is that in the last lecture we found out that the conditional variance of a Bernoulli distributed variable was the probability times 1 minus the probability. Now, if the probabilities are outside the unit interval, it's not hard to see that this can result in negative variances. So we get these kind of awkward predictions from the model that you can have like negative variances, and you can have probabilities that are outside the unit interval. Okay? Then on top of that, here you see even those negative predictions. Well, that's one thing, but another thing is that the conditional variance here depends on x. So what does that mean? Well, this is like, from you've seen this in econometrics A. What if the conditional variance depends on X? Well, it's heteroscedasticity, right? Um, if this is like, the error term, the variance of the error term, if that depends on X, well, you got heteroscedasticity. If you have heteroscedasticity, we know that OLS is inefficient, and the OLS standard errors are biased. Okay, so they're invalid. You cannot use the standard formula for the OLS standard errors, which would be the X prime X inverse times the residual variance. You would have to adjust those standard errors, find another estimator that is not inconsistent. So that's generally possible. You just have to use the sandwich formula to get heteroscedasticity robust variance covariance matrix for the estimator. And for, you already seen that formula in chapter 12 when we went through nonlinear least squares. Okay. So those formulas do exist. It's just one thing you need to account for when you estimate linear probability models, account for heteroscedasticity in estimation of the standard errors. It's still inefficient, and you may ask, why don't we just do like something like weighted least squares, where you weight the observations with the standard deviation of the residual standard deviation. Well, in principle, you could do it, but it kind of becomes a little bit awkward once those estimates of the conditional variance becomes negative, right? Then you start weighting with negative numbers, and not good. Okay, so really that's in short some of the issues you have with the linear probability model. What people do is really just estimate the linear probability model with OLS, and then use heteroscedasticity robust variance covariance matrix for computation of the standard errors. And then do not try to take predictions outside the unit interval for the probabilities as too little. So we're going to try to see if we can actually estimate this model, and to try to see first study some of the properties that we're going through here. I'm going to try to illustrate that with some simulated example, and then afterwards we're going to try to see if we can estimate a linear probability model on some microdata. Okay, for that we need to import a bunch of libraries that I'm relying on in this code. I have to warn warn you guys, I'm really a terrible Python programmer, so this could probably be done much better. But this is what we have to work with. Okay, I'm relying on a bunch of non-intrinsic libraries that you may have to install if you're not done so already. But you should just uncomment, be able to uncomment here. And then you'll see it starts to install. So here for me it's already installed, so I don't want, I uncommented that. Okay, but I'm reading in like NumPy, some stuff for tabulation of results, random number generator from NumPy, put that into random. I need the normal distribution, some plotting, and then linear algebra, I call that LA for short, and then some statistical models. So these things you would have to do as well. And by the way, I assume everybody would have access to this to this Python notebook, and I really encourage you to go in and modify and play around with it yourself. I mean, that's really how you really learn how to actually do it and understand the meaning of each of the equations that on surface can be a little bit abstract. So the first thing we're going to do is we're going to simulate some data from a binary response model and estimate that with a linear probability model. So what I'm doing here is I'm simulating some binary response data. And actually, I'm not simulating it from the linear probability model. I'm simulating it actually from a probit. So I'm not going to go so much into detail with how it is done. Just say a little bit about the model. It's a model with one explanatory variable So and a constant. So we generate an explanatory variable x1 and a constant, and that explanatory variable x1 is just normally distributed, and we got n observations of those. Then we collect those two into a matrix. This is what we, our X matrix that we when we that appears in x prime x inverse x prime y when you want to do estimation. So we have that right here. I mean, you can always go. Actually, I really encourage you to do that. Like go in and say, just print what is in this stuff here. Like so, X sim here looks like this, and then you see here we got this column of ones and then some normally distributed variables that are really x1 in the second column. So this is how that looks, and you can see the shape of it is 10,000 by 2 because we have 10,000 observations and 2 explanatory variables, a constant, and then x1. And you can also look at the shape of y, which is n by 1, and look a little bit at how that is looking. It's a binary outcome that's generated by this function here. And so here it's really what makes it binary. So basically I take x times beta, which in our case would be, since beta is 0 and 2, would be 0 times the constant. So the constant doesn't matter here. And then 2 times x1, okay? And then I add an error term, which is normally distributed. And then whenever that is positive, well, then it returns ones. Otherwise, it returns 0. And actually, this is the probit model that we're going to look at later. So since I've not explained it now, I'm not going to dwell too long with it. Just think of, we have some binary outcome data simulated on the computer. And then we want to look at how the linear probability model can help us actually uncover the effect of x1 on the probability that y is equal to 1. Okay, so that's all good. So with that, we're going to move on and do a little bit of plotting. And there's a bunch of stuff going on here. And you can go in. I mean, that's going to be a little bit tedious to explain all the code here, but you have it here for reference. The key thing is I'm taking in here the data, the binary outcome, and then our explanatory variables, the matrix of explanatory variables, and then true values of the betas because I need that for plotting. And then I estimate a linear probability model here using OLS and do a bunch of plotting. It's yeah, why don't we just look at it? That's better, okay? Because this is basically just calling that function here, okay? So this is the first graph here is generated by this block of code here, okay? So what we have here is basic plotting the simulated y against x1, okay? And you see here really as x1 is increasing, well, you get more and more observations that are of the response variable y that is equal to 1. Okay, it's certainly not looking completely linear, right? But it does appear that as x is increasing, so is the number, the probability that you get y is equal to 1. Okay. And you see here, down here, for instance, there's no observations of y where y is equal to 0 when x is very high, but there's a lot of observations where y is equal to 1. And that's kind of expected because the coefficient on x1 was equal to 2, so the probability should increase in x1. Now, so that's just a scatter plot. Now, what I've plotted here is actually the underlying response probability that was used to generate the data. Okay, so this is not a linear response probability, not at all. It has this S shape, and this is how it would look in the probit model. But this is what was used to generate the data. So you see like there's almost a probability 1 in this area here, where you have also only observations of y is equal to 1. Now, what do I plot here? What I plot here is the estimated coefficient times x1. So basically the predicted value x beta, our model for the estimated model for the probability. You see it's linear. This is why it's called the linear probability model. Okay, and you can also see here that it is predicting probabilities that are negative. Okay, when x1 becomes very low, well, you got negative probabilities. You also got predictions of probabilities that are larger than 1. So here you got 1. Well, there's a lot of there's some predictions out here that's above 1. So this is that's an artifact of having a linear model. Unless the coefficient is 0, it's gonna have to go outside the unit interval at some point. But what you also see is that it's kind of on average tracking pretty well what is going on. And this is what I alluded to just before, that it's actually getting the average partial effect in the sample pretty well. So on average, it may not get that the partial effect is constant in linear probability model. There's a constant slope. It may not get the slope of the true underlying probability right, but on average, if you average over all the observations in the data, the slope of this curve, it's going to actually be quite close to the slope of this curve. So if your interest is really what is the average partial effect, well, then the linear probability model can be a pretty good approximation. Then the last thing I want to allude to here, this is our plotting of the conditional variance. You know, the formula we had right down here. This is the conditional variance I'm plotting. Where do we have that? So I put that in as a last plot here. So you basically have x beta times 1 minus x beta, and then I plot that against x. So what you see here is, again, as you get predictions of probabilities that are negative, then which happens around 1.5, well, then you also get negative variances. Okay, so here, all this area here, you got negative conditional variances of from this model, which is not something we would like for econometric models. Okay, and it would make any attempt to do weighted least squares using our estimates for the conditional variance as weights infeasible. So this is kind of illustrating some of the issues with LPM graphically. And actually, I mean, you can. I really encourage you to go back here, and that goes with anything here in the code, and try to, you know, what would happen, say, for instance, if I change the coefficient here, right? So then simulate the data, and then go back and plot it, and you can see now here, now it's much less clear. There's much more overlap between the two outcomes. The response probability is not it doesn't have as much S shape as before, because basically the partial effect of x1 is now essentially lower. Okay, so these are things you can like play around with. Okay, so let's just, you know, move it right back to 2, so that everything is like restart. Okay, so that was a simulation exercise, simply just to that was a simple simulation exercise to illustrate some of the properties of the linear probability model, with negative variances, with predictions outside the unit interval, and with the fit of the linear probability model being actually pretty close to the average partial effect. We haven't really showed that yet, but we're going to show it later. Now, I want to move on to talk about some real data and use the linear probability model on some real application. And for that, I'm going to use the data set that comes with Woolrich's textbook because it gives us an ability, a chance to replicate results that are in the book, so you can really see, okay, if I type in the formulas correct, do I get the same as an experienced guy like Jeff Rubich? Okay, and then we can also talk a little bit about the empirical work. So what is it we are trying to model here? Well, we are basically we get a data set. So we read in that data set here. It's called MROS. You can do that once you've imported Woolrich and appropriately installed it with your pip statement. Our response variable, that is a binary response for female labor force participation. So this is equal to 0 if that particular person is not in the labor force, and it's equal to 1 if that person is in the labor force. Okay, so that's our binary response. Okay. Then we have a bunch of explanatory variables, and there's more explanatory variables than just these in the data set, and you can also try to see estimate other versions of this model. But these are the explanatory variables that are used in example 15.1 in the textbook. Okay, so we collect all these data and then put them into X together with a constant, and then we can describe those variables here. Basically, here I add both the dependent variable and the explanatory variables, and you see all these here. And then we got a little bit of summary statistics. We got 753 observations, so this should be doable on any of you guys' computers. And here you see on average 57% of the respondents are participating in the labor force. Variables are between 0 and 1, okay, because it's a binary outcome. Then you got here the non-wife income. So this is for married women's labor force participation. So you may think that the husband's income or other income in the household is affecting the probability of participating in the labor force. You have education, experience squared, age, and then the number of children lower than 6 years old, less than 6 years old. So and kids older than 6 years old. And you can see there's some people who have like 8 kids, but it's not a lot of people. But it's like going between 0 and 8 and 0 and 3 here. So you can look at those descriptions. It's always a good idea to make it like a quick description of the data so that you know what you're doing. Now, we didn't come here to do descriptive statistics. We want to estimate binary response models. So, and we want to do that using these data. Okay. So why don't we move on to the next slide here? So again, we can estimate the linear probability model here with just OLS. Now, our X variable here is now 753, I think, wasn't it? 753 by 1, 2, 3, 4, 5, 6, 7 matrix, okay? Plus the constant, so it's 8. Okay, so this means that we have 8 explanatory variables here. Okay? So we have 8 also 8 coefficients, and the reader who has the book, looks like this, could go to that page, find out, and see that it actually matches. So we've replicated some results from the book with OLS. Now let's move on, because as I alluded to before, this estimator is very simple to estimate, but we need to do heteroscedasticity robust standard errors. I didn't actually code this up here, but I leave it as a very nice exercise. I think maybe you're actually doing that in the computer lab. So I don't want to take all the challenges away from you. Now, this is implementation using simple linear algebra, just creating a one-to-one relationship to the formulas in the book. But you can, of course, in Python, there's other people who have coded up the linear regression model. So you can find lots of canned routines. So for pedagogical purposes and teaching purposes, well, it's not giving you that one-to-one relationship, but it's giving you something to replicate, so you can match and see if you can replicate those results. So here's what you get if you use these statistical models module that you can get in Python. You can see the documentation here. And do OLS regression of the same model. Okay, so here we get the same coefficients as we just had over here. So 0.58 and minus 0.03 for non-life income. These are exactly what we have here. And the standard errors, well, here you can add the option of getting heteroscedasticity of robust standard errors. So now if you're going to try to see if you can replicate those using the sandwich formula, you have something to compare with. Okay, which is a kind of a nice way to try to see if we can understand some of the formulas. Okay, you got an R squared and a bunch of other things you can practice on, see if you can replicate these results if you feel like it. We're gonna move on from here. This is kind of our initial treatment of a linear probability model, and then move on to the next topic, which is the latent variable model. The latent variable model gives a nonlinear prediction of the response probability, and we'll talk about that in the next video.